We are starting our next chapter, chapter 6. Give you a heads up. There's quite a lot of work in chapter 6. It's going to be a 1 week deal. Normally you get 2 weeks, but this is a 1 week deal. And the reason it's a 1 week deal is that after chapter 6, a week today, you're going to get your midterm. Right, so that's pretty much what's happening. So this Sunday, you have to get all of chapter 6 homework complete. So don't think, well, I can maybe, no, I'll do it next week. That's not going to happen because it's not going to be due next week. It's going to be due this week. So this Sunday, all of chapter 6, it should already be online. So if you want to look at what's in it, you certainly can. As I say, there's a lot of work in it. And so let's get started. So what's chapter 6 going to deal with? Well, it's going to deal with what's called the normal distribution, its uses and applications. And just as I started talking, 2 more people turn up. Okay. So let's show you what it looks like. Can you imagine that you do a histogram and it looks like that? I guess you would call that what, a mound-shaped distribution, right? A mound-shaped histogram. I'm just using the word distribution here. Agree? It's one hill, evenly split, symmetric. That's an example of what we call a normal distribution. So just a new name to a mound shape, right? So can you imagine you collected a population, and these curve shapes are really just representing what a histogram would look like, right? And nobody wants to keep drawing rectangles, so we just do the smoothed off version. Now, what kind of properties does this type of shape have? Well, right in the center, you have the mean. And we're talking about a population here, so I'm going to use the mu guy. Remember the symbol that you pronounce mu, the mean of the population. And it has been discovered numerically, sometimes the word empirically is used, that these distributions all tend to have the same kind of shape and property. Now, if you take one standard deviation away from the mean, so one standard deviation is sigma, and if you go the other way, you do one standard deviation, you get to these 2 guys. And these guys are nu plus sigma, and this guy over here is nu take away sigma. And if you do 2 standard deviations, you get to here. And if you do 3, you get to here. So I'm going to do a clean version without all those rectangles on it now. The typical distribution, normal distribution, from start to finish, 99.7% of the data is always in that range. So if you have a mean and a standard deviation, you get plus or minus 3 is the guy you get. Right in the middle is the mean. And just because I can, I'm going to choose different colors. One standard deviation to the mean takes you to here, to here. And what color shall I use now? Blue, I guess. And 2 standard deviations, either side of the mean, takes you to here and to here. Can you imagine I drew that a little bit more symmetric? But it's basically, that's what the normal distribution looks like. It's a nice mound-shaped curve. It's got a lot of symmetry on it. And if you do 3 standard deviations either side of the mean, you typically get pretty much all of the data. So suppose I have a normal distribution. Oh, let's say the mean is 100 and that the standard deviation is 10. And I wanted to draw what that distribution would look like, even although I've only been told that it's normal and I'm being told this value and this value, we can do a pretty good representation of what it would look like. Draw that picture like that. Right in the middle, that would be at 100. Actually, this is the distribution for IQs. You ever had an IQ test? It's mean as 100, its standard deviation typically is 10. And then if you, oh, you've read that. You go 110, 120, and right at the end, 130. And if you go the other way, right there, you go 10 off that's 90, 10 off that's 80, and right at the end is 70. So if you collected, oh, I don't know, a million people and you gave them an IQ test and you made a big histogram of it, this is what the histogram would look like. And not only that, can you see that there's a good feeling about the range of where the numbers start and finish? The vast majority of people have an IQ between 70 and 130, right? 3 standard deviations away from the mean. Now, if your IQ is more than 3 standard deviations away from the mean, so in other words, it'd be living out here somewhere, it's an outlier. So if you have an IQ that's more than 3 standard deviations away from the mean, that's an outlier. Now, unfortunately, for some people, couldn't your IQ also be less than 3 standard deviations away from the mean? And they are also considered an outlier. So the vast majority of the human population live somewhere in that range. And don't think of people whose IQs are low as being stupid, or people whose IQs are high are being really clever, because IQs really doesn't measure what the name suggests it measures. It actually doesn't measure your intelligence. It's called intelligence quotient. What it really measures is your...
class.
Hello? A question? Okay.
No, leave them down here. They're vacuuming.
I am going to just mute these because we don't want to hear people's conversations. Okay, there we go. So I was saying it doesn't actually measure intelligence quotient. It measures how easy it is for you to learn. Oh dear. Someone just turned up, so I had to go back out and then again. It's a real pain. The only way I can let people in is by closing my window and then going back out and then. So if you're getting dizzy, that's what's going on. As I was saying, for the third and final time, I hope, it doesn't measure intelligence. It measures how easy it is for you to learn things. So you might think, well, doesn't that mean kind of the same thing? Well, sometimes it does, but not completely. I have met some really intelligent people in my life, I mean, exceedingly intelligent people, but they're as lazy as heck. And they don't study, they never studied, and they dropped out of university. Just couldn't be bothered. University was just too much fun. Why study? Why turn up in classes? And so those people crashed and burned. And there's a lot of people who have a very high IQ, but actually know very little, because you have to put in work to learn stuff, don't you? It doesn't just appear in your brain without you thinking while you're sleeping. And the other extent, some of the most successful students I have met have not been necessarily the ones who had a high IQ. And very often having a slightly lower IQ can be an advantage if you have the motivation behind it. And so the story goes something like this. You go through college and every math class you get is hard. You have to work at it, you have to do practice, you have to think about it, you have to watch other videos, but eventually you get there, right? But you get there. And you graduate and you go to university, and when you go to university, the math classes are really hard, but you're used to that. So you just do your process of studying, working at it, looking at it different ways, and you get through. Have any of you met a student at high school who was really intelligent and they used to annoy you by turning up on the day of the exam and saying things like, I can never bother to look up anything, I can remember it. And then they get 90% and you fought like murder and you got 85 and the world's just not fair. You ever had that kind of student? Or knew about? Right. Well, the sad news is a lot of them don't make it. And the reason they don't make it is not because they were bright, because they obviously were, but eventually everybody will hit some math that's really hard. Now, for those who math is always hard, they don't notice the difference. That's the way life always is with math. But what happens to a really bright person is when they hit something they can't understand or don't know what to do, they don't have the skill set of how to tackle that because they never did review things. They never did have to go and think of other ways of doing it. So my advice to you is that hard work is much more valuable than God giving you a nice high IQ. Well, let's put some numbers on this because there is some really quite amazing information that I haven't shown you yet. And I'm going to take a copy of it right now. In this region in here, 34% of all the data lies. And in this one over here, it's also 34. In this next chunk, this little piece of pie between here and here, in here, there's another 13.5%. And then in that little piece at the end, in here, there's a 2.35%. And over here, there's a 2.35%. What this does is that it allows us to put a predictor on what percentage of people will have certain IQs. I kind of imagine this as being a cake and you're cutting out bits. So to give an example, if I went and said to you, what percentage of Americans have an IQ of 110 to 120? And the answer is 13.5%. If I went and asked you had an IQ of 100 to 120, can you see that you add 34 and 13.5 together? And that's 47.9%. 47.5%, sorry. So as long as I give you a number in this bottom list, couldn't you find out what percentage of Americans have an IQ in that range? That's pretty useful to know. Let's try one. I'm going to give you a start number. It's going to be 80. And a finish number is 110. So hopefully you can see my picture with the details on it. So what percentage of Americans have an IQ between 80 and 110? Give you a few seconds to work that out.
$80.5?
Here the 8.5. Let's see how that works. Well, I hope you said, okay, that little piece of cake is 13.5. This piece is 34, and so is the piece next to it. And that's 68, 78, 80. I think it's 81.5. But I don't trust my own counting here. Yeah, 81.5. So you're probably doing it right, just didn't quite add it up. Now, only knowing that it's normally distributed, right, that it's got a mound shape, only knowing that plus the mean and standard deviation, you can create a picture like this, right, with 1, 2, 3 standard deviations forward and back. And from that picture, you can actually make a whole load of decisions or a whole load of estimates on what percentage of the entire population had whatever the range is. Now, in this table up here, what percentage of the people do you think have an IQ of 100 or above? But don't bother adding the bits up because that won't help you actually. What percentage are the mean or bigger? It's a nice round number.
50.
Yeah. And won't the mean or less be the other 50? Great. Now, if you add up these three numbers, they do not add up to 50, right? They're just a little bit shy of 50. And the reason they're a little bit shy of 50, aren't there a couple of really weird outliers? Weird's a bad choice. But aren't there a lot of really large or small outliers that are still not included in this picture? But you could theoretically, couldn't you just flatten that curve forever? So there's no particular stopping point. So stopping at 3 is kind of the nice place. That's where we stop. Right, 3 standard deviations either side. Now that same table can be converted into this fella. And what it's saying is if you go 1 standard deviation, then you go 2, and then finally you go 3. So if you are 1 standard deviation either side of the mean, 68% of the people have an IQ in that range, right? The 238s basically, right? Now, if you go 2 standard deviations either side, that adds up to 95%. And if you go 3 standard deviations either side, that ends up being 99.7%. So can you tell that the little bits at the end are, what, 0.3% shared equally, all right? About 0.15%, tiny amount, hardly anybody in that range. Is there any questions so far? Are we comfortable about this? Mound-shaped curve has all sorts of structure to it that we can actually use. Looks like I may have a question here, so I'm going to go out. Okay, so back to this guy. Are we good so far? Right, so I'm just having a quick look at what we need to be able to do. Okay, so I'm going to take some questions from the homework, some of the numbers and the questions from it. What one am I picking? This one is a version of question 7. assume that the heights of college women are normally distributed, right? So they look like that, and that the mean is 60 inches, and that their standard deviation is 2.9. And then they give you a version of my really badly drawn picture, like this guy here, to help us. So we're being asked what percentage of women are taller than 60. Well, let me draw my picture first before I start looking at the questions. Right in the middle goes 60, okay? Then you go one standard deviation. So this guy is going to be 62.9. Agreed? This one here. And then add another 2.9, and that's 65.8. And then to finish off with, add another 2.9, 67, 68.7. And then going backwards, something like this. Take away 2.9, and that's 57.1. That's what calculators are for. So I'll do the next one that way. If you take 57.1 and you remove another standard deviation, you get to 54.2. And then if you remove another standard deviation, you now get 51.3. So to be able to answer these kind of questions, you got to build one of them, right? And then you might just want to have a blank one of these guys, right? Because they contain all the separate little pieces that you're going to add up, right? So now that I've got that, I can look at some questions. One of the questions says, what percentage of women are between 57.1 and 62.9? So if I look at my picture, aren't we talking about those two pieces of cake? 57.1 to 62.9. Right, what percentage of people live in that piece of the cake?
64%.
60, how much again?
4.
Can
No,
I-
wait, no, it's 68. 68.
Gotcha, 68. So the answer that they're wanting in your box is 68%. Now, if you're wondering where that came from, I cover that up. 57 to 62.9, isn't it these two pieces? You go over here and you find out what these two pieces are worth, add them together, 68. Suppose they wanted 54.2 to 62.9. Right, so it's a little bit different, but not much. What's 654? Yeah, so 54.2 is here. So I'll put a little shade on it, right? And then we got this piece here, and then we got that piece there. Would you agree it's 3 pieces of cake? 54.2 to 62.9.
81.5.
Right, so those two in that one, and you said, I'm sure you did say the right answer. What was it again?
82.5. 81.5.
81.
81.
Okay. Use a calculator like me if you're careless, right? Just to be safe. So if I tell you the mean and standard deviation and it's normally distributed, hopefully you can create one of these pictures, right? With the 1, 2, 3 either side. Once you've got this picture created and you've got a blank one of these so you know what each one's worth. I mean, I could just go to this question and write that's worth 34, that worth 34. This is worth 13.5, that one's worth 13.5, and this is worth 2.35, and so is that one, 2.35. I guess I could do it that way, right? But whatever way you do it, isn't it just a matter of tell me where to start and tell me where to finish, and therefore I should be able to calculate what percentage of people are in that range. So here's my last one, which they haven't given you, but I wish they had. 54.2 or bigger. So anybody who's taller than 54.2 inches. Well, if you look at 54.2, isn't it this guy and this guy? Right, those two. What about the rest, which is what this is? I don't really want to count these up. Can't I just know what this whole chunk here is? How much is this whole side, the right-hand side, worth?
Percent.
50.
50. So don't I really just need to go something like this? This piece, 13.5. This piece, 34. This piece, 50. And that would get me the answer. So can you imagine that in most situations it's going to be just adding up pieces of the pie? But can you imagine if it's a less than or greater than kind of story, it's much better to just say that half is worth 50 and then just, whatever's left. So in this case, that's what, 68, 78. God, that's hard to do in my head. So there's a 5. There's a 7. Yeah. Evidently, 97.5% of women at college are taller than 54.2 inches. For what that's worth, that's what it is. Are we cool? You feel comfortable about how that process works? Okay, then I am going to go and switch us over to the homework, and we'll do a quick scan through and see if there's anything that maybe I could have covered a little bit more. That's not what I wanted to do. I wanted to go here and do that one. Okay, here we go. I'll scroll up to the top first. See how many questions there are. Right, there's 12 questions. This section is pretty quick. Next section is going to be a bit slower, but not much. And the book likes to give you weird kind of thought questions. So here are 4 pictures, right, of a distribution, 4 curves, although that's not really a curve, but whatever. We got to look at which one of these is actually considered to be normal in shape. A, B, C, or D? Which one do you think is the closest to being normal in shape?
D.
Yes. Which is the least curved of all of them, isn't it? But to be a normal distribution, it doesn't need to be perfect. It does have to have a couple of features. First feature is it's got to be symmetric. And the second feature is it's got to be unimodal, right? One hill only. So I'm picking D, and it's normal. And that's all I say. Okay. What do you think's wrong with C? Because it definitely is symmetric, which is good. But what's wrong with C? And here's the choices.
Not normal, not belt shaped.
Yeah. This book has got a nasty habit of giving different names for the same thing. Haven't we been calling it mound-shaped, symmetric? Now get another name for you. Bell-shaped. It's a good name. It looks like a bell, right? I guess that's why it's called that. Can you imagine this one is skewed right and this one's skewed left, and that's why they don't work? They're not symmetric. They're skewed in some way. Right, question 2. Here is a kind of simplified version of the things I was doing, but there's enough there to know what's going on. What number is the mean in this picture? Which number is the mean in question 2?
92.
Yep. What's the standard deviation? What's sigma?
2.
Agreed? From there to there, it's 2. From there to there, it's 2. From there to there, it's 2. which kind of makes this guy a little bit more sensible. That's nice and quick, right? Not really heavy duty work. Here are two normal distributions. Which one has the biggest standard deviation? A or B?
A.
And big standard deviations, don't they flatten the curve, right? If you wondered where that term came from, it's a statistics term. You spread out the occurrence of the illness. Now, if you look at this one, can you tell that the mean of this curve is 10, but the mean of this curve is 4? Now, in this question, they give you a mean and a standard deviation. I may have to shrink this a little. No, I think I get it. I don't know how easy it is to read. It's kind of faint in my screen, at least. But one of these 4 pictures has a mean of 15 and a standard deviation of 2.
The second one, right?
So that one, agreed. And some other questions similar to that, right? Consider 2 normal curves. If the first one has a larger mean than the second, does that mean that it must also have a larger standard deviation as well? Because you have one curve with a mean of 10 and another curve with a mean of 20. Does the standard deviation care what the mean is?
No.
They're independent then, that's the term we use. So one of these is that one. No, whoops, they are independent, right? This one is basically tell me from the the picture with the cut up pieces, what percentage? Is it 34? Is it 68? That kind of question. Same for question 6. There is a nice, pretty, much better drawn than me, coloured picture of the guy I was talking about. If you've got that guy in front of you, couldn't you just draw your number version and then figure out which pieces of the pie you need to add to get any particular value? So if you wanted to do 57.1 to 62.9, if you were doing that, wouldn't you make this one 60 and then go up in 2.9s? And from 60 go down 2.9s. And then you'd know which, it's this piece plus this piece kind of trick, and you're done. So we have covered that. There's another question, same idea, third one. Okay, I think I'll do 10. At Burnt Mesa Pueblo, archaeological studies have used the method of tree ring dating in an effort to determine when prehistoric people lived in the Pueblo. So from what I've seen on TV, don't they use basically trees and mud and brick to build their houses, right? And so you get a tree and you cut it and you can actually identify how old that tree was, how far back in time it was cut, really. And from that you can date it. Wood Shrivel gave a mean of 12, good grief, that's a long time. 1,233 years ago, and the standard deviation was 27 years. And then it asks us, at what range of years centered about the mean is about 68 of the data going to be? Well, isn't 68 1,233 take away one standard deviation, and then 1, 2, 3, 3 add one standard deviation, and then whatever that comes to is your range. And how many standard deviations for 95% then? 2. 2, yeah. So mean plus 2, mean take away 2. And they're calling it almost all the data. They probably should have just said 99.7%. And isn't that 3 standard deviations either side of the mean? So I'll not do all of them, but you see this one here, the end one, the big one? Your calculation would be that guy plus 3 standard deviations. So if they use that, what they can do is they can put a kind of age band on how old that particular pueblo is. So at the kind of the outermost range, almost like we're 99.7% sure this is how old this building is. You'd be using this range here, right? The 3 standard deviation one. And you'd be able to say, look, it could be anywhere between 1150 and 1250, you know, that kind of thing. So it's a little bit of a window, but it's at least it's better than we don't know, right? At least it puts a window on. And there's another basic question. And the empirical rule, I know it's here somewhere. I saw it a second ago. There we are. Use the empirical rule. If you're wondering what the empirical rule is, it's the guy that we were doing 1 standard deviation, 2 standard deviation, 3 standard deviation. That's just the name that they give to what we were doing there. Okay, any questions so far? You feel comfortable about 619? Great.
So just one quick question.
Sure.
About the empirical rule and how we decide how many standard deviations it is. How do we do that?
Well, the standard deviations, let me go back to my picture. I can talk about that a little bit clearer when I've got something visual. These pictures that we use, by convention, we do 3 standard deviations every time. So whatever the mean is, 1, 2, 3 this way, 1, 2, 3. So that is guaranteed the kind of typical way that we draw this information out.
And then like when they ask for the range, how do we know which, like how many to use?
Oh, so if they ask for the range, the only question I know that's got a range in it is one where they give you an example of the range is this guy, take away that guy, right? I'm not sure if that's the question you're talking about. Is it a specific question?
Like the Pueblo one?
Mm-hmm. Also, the range would be, for instance, in the Pueblo one, you've got the mean, 1233. You add 1 standard deviation either side, and that range, well, I could do that one. If you did the 68% one, right? So what range of numbers would 68% of the 3 rings be found? And the answer for that one is the mean plus or minus 1 standard deviation. So that's 1233 plus or minus 27. And so on the big side, that's 60, 1260. And on the small side, that is 1206. So we would say the range was that number to that number. So they're using the word range here in the kind of general English way, rather than the range is the largest number in the data set, take away the smallest number in the data set. That word range is a different meaning to this word range. This is just the spread. See, that's another problem. If I said the spread of the numbers, wouldn't spread sound like I was talking about something to do with standard deviation?
I guess I'm still kind of lost on the part of like the 68%. And
okay, what we've told you is that there's a lovely property that every single normal distribution has. If you take the mean, which is here, and you add and subtract 1 standard deviation, as we did here, you get numbers that are from 1206 to 1260. And
Right.
what we know, the empirical rule says that
Oh, that
we
will
have
always,
found,
it would always be 68% in
yes,
most normal distributions.
in every normal distribution, that will be 68% within the realms of, you know, variability that you get in every world situation.
Okay, that makes sense. Thank you.
Right. And when you do 2, you get 95% all the time, right? Every normal distribution, 2 standard deviations away from the mean, you typically get 90%. If you go crazy and go to 3 standard deviations, then sometimes this book will say almost all. It really should say 99.7% of the data, which is kind of almost all, isn't it? But I prefer
I
a
see.
number.
Great. Well, that helps. Thank you so much. I got it.
Yeah, you got it. Cool. So we are now going to be looking at 6.2. It'll give me a few moments to set up the homework thing so it's ready when I need it. Where the heck are you? You here? Nope. Okay, I'm going to have to shut you lot off for a second. Okay, just waiting for something to load up. That looks good. Right, I'm ready now. This may have been here all the time. Looking at 6.2, area under standard curves. Its full title is a standard normal curve. And that's kind of the second part of today is going to be developed with. So let me give you a problem that this eventually will solve, although we can get the answer even before we get there. John and Mary are twins. We didn't know that, but they are. John took an English exam and he got a score of 80. And Mary, she took a math exam and she scored 80. And they were both arguing about who did best. Now, before you did statistics, you would probably say they both done equally well. They both got 80. But Mary argued with John and she said, I did better than you. And the reason I did better than you is that this math exam was much harder than your English exam. And John's not convinced. And if this is the only information that you've got, plus somebody's subjective view about how hard math is compared to an English exam, you couldn't answer that question. But they do have some information. John found out that the mean of the English test was 70. And Mary found out that the mean of the math exam was 70. And so John went and said, see, I told you, we both did just as good as each other. The average in my English class was 70 and I got 80, so I did better than average. And you got 80 and you did better than the same average. So we did exactly the same. Seems reasonable. It's also going to be wrong, because I'm now going to tell you the last piece of the puzzle. In the English exam, the standard deviation was 10. And in the math exam, the standard deviation was 5. Standard deviation is important because it tells you how spread out the data is, right? So I'm going to draw a little picture of these using our normal distribution technique, and I'm going to try and convince you. Well, before I tell you who do you think did better now?
Mary.
Mary. So I'm going to try and convince you that that's the case. So I think I know the best way for me to do this would be like this. So right in the middle, we've got 80, 85, 90. There we go, 70, 75, 85, 90. Don't really need to go much further. Right, oh, I guess I should go these two just for completeness sake. If I put a dot here, and can you see that? No, darn it. Can I take this back? I should have thought this through. I didn't give myself enough room to do 3 standard deviations, and I needed to do that. So I should have. So right in the middle, this is John. There's 80. Now, since the standard deviation is 10, won't the people in John's class now, you might say 110 is impossible, but can you imagine the test was out 120? Like there was extra credit or something, right? You could get better than 100. So this is John, and this is English. Right underneath it, there's 80. That's 80. Oh, shooting space. You know what I've done wrong, don't you guys?
The mean is 70.
The mean is 70. I'm trying to figure out the easiest way of fixing this. And the only way I can think of doing it is a mess, but it's better than redrawing the whole picture again. You know, your job is to keep me on the straight and narrow. And I should have probably noticed when 110 happened that something wasn't right. Okay, with that little hiccup, are we okay now with that being what the distribution of scores in John's English class would look like? Okay, so I can now at least start with 70, right? I'll put 80 here, I'll put 90 here, I'll put 110, 100 here. And then going back, I'll put 60 here, 50 here, 40 here. But there's going to be a difference. Because their standard deviation is 5, 75, 85, 65, and 55. Do you see that this data looks like that? Now, if you put in a little line at 80, can you see that there's a big chunk of people in John's class and there's very little in Mary's class? Can you see that's much harder to get 80? It's further to the right. And that's the trick. We don't want to have to, of course, as you can see how bad I do it, to have to draw one of these pictures every time we get that question. And so there is a way that we can do it. We calculate a thing called the standardized z-score. Everybody just calls it a z-score. And it's a number that tells you how many standard deviations away from the mean the score is, the data is, that's a better word. What does the Z-score formula look like? Well, if you want to do it in English, it's the data, the number, take away the mean, divided by the standard deviation. The algebraic way of writing it is that. So we are going to find the Z-score for John and Mary again. So here's John first. He got a score of 80. The mean was 70 and the standard deviation was 10. So the score for the Z-score for John is 80 take away 70 divided by 10, and that's 1. So John was just 1 standard deviation away from the mean, right? Which is good. Let's see what Mary looks like. Well, she had a score of 80, but her standard deviation was 5. So when we get her Z-score, we get 80 take away 70 divided by 5, and we get 2, which means that she's 2 standard deviations away from the mean. Now, the bigger the Z-score, the harder it is to get that thing, right? So it's harder for you to get 80 in Mary's class than it is to get 80 in John's class. Because in Mary's class, don't you have to be 2 standard deviations away from the mean? And that's typically harder to get because it's further away from the center, right? Where all the usual people get their scores. Right, apart from the fact I get really caught up in my pictures, we now have a very, very good test to compare 2 things in a much fairer way. Give an example. SAT scores. Do you know that the SAT score that you get isn't actually the real SAT score that you got? It's standardized from one year to the next to make sure that every SAT score is basically got the same distribution. Because, you know, sometimes one year the SAT test is a little bit hard, and so the mean and standard deviations, you know, reflect that, and sometimes they're a bit easier, and that happens as well. So whenever you hear things like grading on a curve or standardizing something, they're using these Z-scores as part of that process. So let's invent another present story, but we're going to make it a little bit more complicated. Donald, who is me, and David is one of my brothers. I got 50, and my brother David got 60. So that's our score. And we took a math exam, but we took it with different professors. And in my professor, the mean in the class was 40. And the standard deviation was 10. And in David's class, the mean, whoops, don't you put that down. The mean was 50, and the standard deviation was 5. Now, same kind of question. Which one of those 2, me and my brother, did better in the exam? Well, isn't the average of David's class bigger than mine? But isn't the standard deviation smaller than mine? And both of those contribute to how hard it is to get a score, right? Both of them are. One on its own is no good. Both do matter. So here's the Z-score for me. And it's x take away mu over sigma. I got 50, take away 40, and you divide it, and I'm making my life easy, that's 1. And here's David, my brother, and let's see what he got. What did he get? Well, he got 60, take away 50, divided by 5, and he got 2. So conclusion time. Who did better? Me or my brother?
Brother.
Yeah. Now, what we've done here is we've taken value judgments out of the picture, where people just have a value judgment. Well, that class had a higher average than you, so that makes this less likely or more likely. Because when you only look at one piece of the puzzle, either the mean on its own or the standard deviation on its own, do you know you can come to the wrong conclusion? You could argue, well, okay, he got 50, but his class had must have been a harder test because look, the average was only 40. So he did really good, right? Well, you got 60, the average is 50, but that 50 is bigger than 40. So that meant this was an easier test. So 60 was easier to get, you know, that kind of argument. And the standardized Z-scores take that totally out of the way. You can even use Z-scores to check for outliers. Suppose we had a basketball team and the average height was 72 and the standard deviation was 4 inches. And a new player is coming to join their team. And we're wondering whether he's an outlier. Well, actually, we'll have 2 new players come to the team, make the story more interesting. Player A is 79 inches tall, and player B is 65 inches tall. And the question is, are either or both of those exceptionally different compared to the rest of the people in the team? Well, let's get the Z-score for A. The data, take away the mean over the standard deviation. That's 79, take away 72 over 4. And now we're going to get 1.75. So it's about 1 3/4 standard deviations away from the mean. And the other guy, well, he's going to be 65, take away 72 over 4. And that's negative 1.75. What Z-score do you think makes you an outlier?
Negative.
No. Negative on its own just means that you're smaller than the average, but that's not a big deal. Do you know that half the people are always less than the average? Do you know half of America are below average height? Half of America are below average age. Half of Americans are below average intellect, because the average is the middle. And anything that's less than the middle, because of the calculation, will generate a negative score. Now, what Z value is big enough to make you an outlier? I kind of touched on it superficially.
Over 3?
Yeah. So none
Or
of these
under
two guys,
-3?
or -3 on the other side, but 3 is the important number, Denise, so you nailed it. Right, none of these two people are considered outliers in the basketball world. I bet you that definitely A and probably B would be outliers in the normal population world? Would you agree that basketball players, just by the fact that many of them are really tall, are exceptionally tall, right, in the outlier range of tallness, rather than just somebody who's, you know, a little bit bigger than everybody else, exceptionally tall? So we have a way of quantifying how unusual a particular score is, or height, or whatever it is you're measuring. And we do it by this thing called the Z-score. Is that cool? Any questions?
Can you move the paper that's on the right side up just a little bit? There we go. Thank you.
Right. Okay. I'll give you an example how we could use this in a practical sense. Can you imagine a university has two professors, two English professors, and one of them, nothing can be perfect. There hasn't been a novel that didn't have something wrong with it. There's never been an essay that's perfect. And because of that, you never get an A. Right? It's just tough. You can't get an A. And he might be quite rough on even minor things. So can you imagine if you got that English professor, if we just relied on the score that he gave you out of 100, right? You know, I've never given a student more than 90% in anything, you know, that kind of professor. That would kill your GPA, wouldn't it? If you had him. If you were just unlucky enough, that was the class you get put into, you're done. And the second professor was free flowing, and almost anything could be good. You know, if you put in the effort and it looked, and he appreciated it, you know, that would be good. So the question becomes, how do you introduce fairness into the grading system? Well, what you can do, and universities have done this, is that whatever the scores people get, we'll assume there's a variation. You know, if everybody gets 100, then forget it. But if there's a variation, right? The tough professor, everybody, you know, if you look at the variation, you know, it's 70 to 90. That's kind of the scores everybody gets. And the other guy, it's like, you know, 60 to 100, right? Well, what you can do is you can find the mean and standard deviation and convert everybody into a Z-score. And so it really doesn't matter what your raw score was. It only matters what your Z-score is. How hard was it to get that number in this professor's class? And then you can just choose cutoff points. A Z-score of 2 or better is an A. A Z-score of 1 or better is a B. A Z-score of 0 to 1 is a C, and anything else is a fail. Now, do you see, if you did that, it wouldn't matter if you got a really rigorous professor or a very free-flowing professor. When you just get an A, a B, and a C, would just be as likely in each class, right? You might only need to get 80 in the difficult professor's class, but you'd have to get 90 in the easier class to still get your A. So Z-scores are very helpful in standardizing things in a, for want of a better word, in a fairer way, right? I don't know, have any of you experienced being in a class where one grade was really high and someone else equally as good as you but got a different kind of situation, got a lower grade, and it just didn't feel fair? You experienced that, or you know someone who may have? This is one way in which that could have been fixed. Any questions about how to calculate what's called a Z-score? The data, the number, take away the mean, divided by the standard deviation. So let's ask you some questions about Z-scores before we continue. If the mean is 50 and the standard deviation is 10, if you get a Z-score of 0, what score did you get what real number score did you get? So imagine this is a test. The mean is 50, the standard deviation is 10. If you get a Z-score of 0, what did you get in the test for that to happen?
50.
Yeah. So a Z-score of 0 happens when you get the same score as the mean of the population. Suppose you get a Z-score that's greater than 0. Then does it not mean that your score is larger than the mean? Would that make sense? A positive Z-score means that you did better than the mean. And a negative Z-score, well, wouldn't that mean you did less than the mean? That makes sense? So positive Z-scores only come from data that's bigger than the mean. Negative Z-scores come from data values that were smaller than the mean. Right, I'm now going to switch over and look at some questions. What does a standard Z-score measure? It measures the number of deviations a measurement is from the mean. So if you have a Z-score of 2, that means that you are 2 standard deviations away from the mean, positive side. Negative 2 means you're 2 standard deviations less than the mean. Right, in question 5, maybe make this a little bit bigger again. Oops, there's my dog telling me she wants a poo walk. Right, in question 5, if I give you the mean is 28 and the standard deviation is 5, and you wanted to get the Z-score for 23, wouldn't your calculation look something like this? 23, take away the mean, which is what, 28, and then divide the whole thing by 5. Will that be a negative Z-score or a positive Z-score for 23?
Negative.
Yeah. Can you tell just by looking at it, it's less than the mean, so it must be negative? Okay. Here's some similar kind of question. Okay. I'm going to have a little discussion with my dogs. What is it? No. Come on now. Let's go. Come on. This way. Come on. Celeste. Sorry about that. That's part of the fun, or the, what's the word I'm looking for? The distractions of working from home, right? My wife's going to take care of the dogs. Evidently, they do need a poo walk. Question 8 is very like the story that I gave you about Mary and John and about me and my brother. And I need to pause here and return back to the screen so I can show you something that I haven't covered yet. If I tell you that the mean of an IQ is 100 and that the standard deviation is 10, and I tell you to find what the Z-score would be for an IQ of 135, then we know how to do that. the z-score is the data, take away the mean over the standard deviation. In this case, 135, take away 100, divided by sigma, and sigma is 10. And I believe that's 3.5, which makes that person an outlier. Here's the new thing that I haven't shown you. If someone has a z-score of 2.3, what's their IQ? So if I tell you their IQ, you can find their z-score. You should be able to work backwards. Shouldn't you be able to figure out what kind of score you would need to get a z-score of 2.3, what kind of IQ you would need? And there is a calculation to do that. And this is what it looks like. X, the IQ score, is mu plus the z-score times sigma. So that's your second formula.
Professor,
Yes,
so you said that 3.5 is an outlier.
correct.
How did you get to that again? How big did it have to be an outlier?
3 or bigger.
Okay, thank you. So,
Good. Now, I know this textbook will probably say 2.5 or bigger, but really everybody in the universe, apart from this textbook, it's 3, right? So let's find out what a 2.3 looks like. Well, the mean is 100. The z-score was 2.3, and that's 10. So that would be, 123. Does that make sense that you can have two specific questions? Here is my IQ, tell me my z-score. Here is my z-score, tell me my IQ. Great. Any questions about that, or are we good? Okay, I'm about to make up numbers here for the next question, but if someone's actually got the real numbers, it would be cool. But if you don't, I'll make up ones. Now, does anybody know what the average body temperature should be for a healthy person?
98.6, I believe.
Right. Now, I'm going to leave for a second, and I'm going to go online, and I'm going to do a very quick search, which may or may not happen, and I'm going to try and find the standard deviation for body temperature. Now, if I can't find this, because I know it does exist, but if I can't find it, I'll just make up a number. And the answer is 0.62 degrees. So what question am I going to do? You might be curious that I went to all that trouble. Well, if you are into the medical field, let's find out what temperatures you need to be an outlier. So how hot do you need to be? What kind of fever do you need to be considered an outlier? Well, what z-score makes you an outlier?
3.
Or bigger, right? And so X should be the mean plus Z times the standard deviation. So in this case, it's 98.6 degrees plus 3 times 0.62 degrees, which I'm now going to do in my calculator. And that is 98.6 add 3 times 0.62. And I get the temperature of 100.46. If you have a temperature, a body temperature of 100.46, shouldn't you be in hospital? Does that seem reasonable? That your temperature is not just high, like I've got the flu and I've got a bit of a temperature. It's like, no, this is worse than just normal temperature, right? This is go to hospital, something really bad is happening. And I'm now going to check that out by doing a quick search online. And I'm going to do 100, I'll call it 0.5 degrees. Body temperature. And we will see what that says. Have a fever over 100? Not good. And according to this very quick article, one of the causes could be that my body is fighting either a virus or a contagion. And this next article says any temperature above 100.5, just that guy there, or higher, is that you are running a pretty decent fever. So do you see, I now have a way of qualifying. If you get your body, if you get a medical checkup, do you know that they'll have a kind of range of values that are okay? And then anything bigger is too high. And anything smaller than this interval is too low. So if it's blood potassium, do you know you can get the mean in 3 standard deviations, and you can say if you're bigger than that number, that's too high. That's danger zone stuff. And then the other side. So it might be within 1 standard deviation is normal range, nothing to worry about. If you move out to 2 standard deviations away from the mean, you're now in the high range. If you move up to 3, you better go to hospital, right? You're in the serious, whatever that is, right? And that also counts if you take -3, agree? Couldn't you have a body temperature hypothermia, right? Which is really cold, and that's not good for your body either. So this is where these Z-scores happen. This is where they live. They are used in a lot in medicine to decide what is considered abnormally big or small. It could be temperature, it could be anything. Do you know when you have a baby? Let's phrase that. When the girls have a baby, because guys don't have babies, at least I don't think we do. When the girls have a baby, won't they weigh that baby when it's born, and won't they take measurements like its height, how long it is? And when they're doing that, what they're doing is that they're comparing that baby's weight and height to the typical average newborn baby. And they have a kind of range of, yeah, that's the normal kind of weight for a healthy baby that's just been born. Or, no, this baby is a little bit on the small side. We should maybe be a bit more careful about it, right? Maybe keep it in the hospital a little bit longer, make sure that it's fine. Because very often those things are an indication that the baby might have had some developmental issues, not mentally, but, you know, just being born and developing. But they don't just stop there, don't they? When your baby's a year, they'll do a same kind of checkup. In fact, all through your maybe you're old enough to actually still remember it happening. But didn't you get, like, you go to the doctor when you were 6 and they would do all sorts of checks on your height and your weight? And that was just to keep an eye on, are you developing in the way that a typical child of that age would do? And if you're outside a certain range, right, too high or too big, then they would say, okay, we would need to maybe look at that. Now, it could be nothing. It could be just genetics, right? Your mum's small, your dad's small. Chances are you're going to be small, right? Nothing to worry about. Yeah, 5'2" is not a bad height. Nobody really cares, right? But then if it could be an indication of, for instance, you're not producing enough growth hormone. And they can treat that nowadays. They can actually give you, if they catch it early enough, they can give you growth hormones, and that can certainly change that process. So your adult height is not that different than a typical person might be. I think we've reached a kind of natural finishing point. So make sure you say hi before you go, because you want attendance. Has anybody got any questions before we disappear?
I just have a comment
Sure.
that was really interesting. I do work at a medical clinic, and the midwives are always saying to call if somebody gets a fever over 100.4, and
Pretty near then, eh?
that's why I guess they do that. I didn't realize it was statistics. It's very cool. Thank you.
Right. You can do it with almost any medical thing. I don't know what, I keep saying blood potassium level, but let's suppose there is a blood potassium mean and standard deviation for a typical population. And then you can say the cutoff point is 3 standard deviations either side. So if somebody's got more or less than that, it can indicate all sorts. And I know, for instance, that mothers, pregnant women have to be really careful about all sorts of blood levels, because that baby that's getting born can really screw up your metabolism. So, for instance, it's not uncommon, isn't it, for mothers to get iron pills, because one of the things baby does is suck out a whole load of nutrients because they're trying to grow, right? And so their mother has to make sure they have plenty. And that's a simple test. You can get a test, and you can check for things like anemia and so on. It's kind of nice when the statistics tells what actually some of you do and it works. I'm kind of pleased about that. Okay, well, unless there's another question, bye-bye. See you on Wednesday.
Thank you, Professor. Bye.
Bye-bye, Raina. Unless you've got a question. You're very faint, so I'm assuming it's bye-bye.